Building. It's building the screen.
That's okay.
Building. It's building the screen.
That's o-
Okay. So yeah, let's start. So
okay.
we're
So
gonna
I'll
talk.
just
Yeah, the remaining articles are just about how to leverage diffusion models to for anomaly detection or defect detection, right?
yes. So I think there were two additional articles that I had added, which I had actually gone over the last few days, which looked
Okay.
fine, but were originally not added because there were others that were also better.
Okay.
So I'll just share the screen. Can you see the screen?
Yeah.
Okay.
Yeah. Starting from this one. Okay.
Yes. So I did actually, I think, had to go over your point on simplex noise, but I'll just do it over the next few days further and then talk to you on it. So before that, I'll talk to you about these presentations. So,
Yeah.
um,
The last meeting we were confused about the motivation, the definition of the motivation of this so-called simplex noise, right?
yes.
Do you have an answer right now?
Yes, I will actually go over it a little bit over the next few days. Right now, I was actually going over the other two articles and also the presentation itself. Um, so I'll just talk to you on it right now. And also, I think there was the experiments that I had to do a little bit. So yeah.
Okay.
So this article is on unsupervised surface anomaly detection with diffusion probabilistic model. In this particular case, the authors basically propose to use denoising diffusion probabilistic models with noisy conditional embeddings to address two shortcomings of reconstructive methods. One is the direct copy problem, where the reconstructive network generalizes well to anomalous samples and hence returns a nearly identical copy of the input sample. This is also observed sometimes with uh, other reconstructive methods which are focused on, let's say, diffusion, but the authors basically come up with a way to avoid this problem and a misalignment problem, which involves structurally diverse reconstruction of the input sample arising due to stochastic nature of diffusion or score-based model, posing challenges for pixel-level segmentation. In this particular case, what the authors are trying to say is that it might be the case that because the diffusion model is trained to generate high fidelity and diverse samples, so the diversity of the samples can also be uh, a key issue where we don't want that the samples are very misaligned which are reconstructed. So that's another point that the authors are trying to address in this case. The overall method consisted of a reconstructive and a discriminative subnetwork, which was similar to DRAME concept with the addition of diffusion model. The reconstructive subnetwork was a latent diffusion model accompanied by the noisy condition embedding. The input to the reconstructive subnetwork was the latent space vector obtained after passing the input image through the encoder of a variational autoencoder. The variational autoencoder was separately trained on the normal data. So we had a separate VAE, which is a variational autoencoder, which was trained on the normal data. In this case, the reconstructive subnetwork attempted to reconstruct the sample which is obtained from the latent space of the variational autoencoder. So that is a key aspect of this method, which tries to attempts to accelerate the process of doing diffusion as well as um, you know trying to reduce the amount of computational cost in that way. And at the same time, it uses a noisy conditional embedding also, which is in the latent space. The discriminative subnetwork produce segmentation maps from the concatenation of the input image, its reconstructive version, and the additional interpolated channels. So in this particular case, they also had a discriminative subnetwork, but the discriminative subnetwork had an innovation in this case, which involved additional interpolated channels along with the input image and the reconstructed image. So that's basically an innovation that the authors have added, and I'll talk about it. During the training process, simulated anomalies were obtained from normal samples and an external anomaly source. The simulated anomalous samples were noised, and the diffusion model output was conditioned on the noisy condition vector. So, in this particular
How is
case,
the discriminative subnetwork um, coordinated with the reconstructive subnetwork?
the discriminative subnetwork basically uses the reconstruction that is obtained from the basically the diffusion model along with along the that's the normal reconstruction that is obtained along with the input along with the input image and various interpolations in between that. So that's where the discriminative network is taking the input. So I have it in the next slide, which is that the interpolated latent sample is basically the anomalous image, the reconstructed version, and these are basically in the latent space, and these are the interpolated channels that are being produced, which are then further passed through the encoder of the decoder of the variational autoencoder to produce images which are
So
concatenated.
C
And
is a noisy image, right?
C is the input, um, is the latent vector corresponding to the anomalous image.
Anomalous image. Okay. And
Yes.
ZR, what is ZR?
ZR is the latent vector that is reconstructed by the diffusion model,
So this
which corresponds
well,
to the,
yeah,
yes.
where does this Z interpolation apply to? In which component it applies to? It applies to discriminative network.
It applies to the input of the discriminative network. In this case, this is also additionally passed through the encoder of the VAE to produce actual
Yeah, yeah, yeah.
images
Yeah.
also.
So okay, so we have a diffusion component, right? The diffusion
Mhm.
component is used to the diffusion is trained on what? On just on normal images?
The diffusion is trained on, um, so that is basically a very good point. In this particular case, the diffusion model is taking normal images along with, at the training process, it's also conditioning it with the simulated anomalies. So that's something that's a part of the training process in this case. The,
So the training includes both the normal images and abnormal images.
the simulated abnormal images that would be they would be conditioned on the simulated abnormal images. So as
Oh,
we can see
I'm
here.
I'm still confused. Like you got a set of normal images, right? You also
Mhm.
have some like abnormal images, anomaly images.
Yes.
And do you use both of them to train the diffusion model?
So in this case, it is possible, in my estimation, possibly those abnormal images can be conditioned into the diffusion model. At the present moment, the method is unsupervised. As a result, it basically uses simulated anomalies as the noisy condition vector on which basically the noise is learned. So it is definitely it should be possible to condition it on an abnormal noisy sample, but at the present moment the noisy condition vector was the simulated anomaly.
So the simulated anomaly, how is anomaly simulated doing this kind of
The
interpolation?
Yes, yes. So the simulated anomaly is basically generated from the normal sample, and possibly the authors were using an external data source in this case, which I think I should have added. Yes, the simulated anomalies were obtained from normal samples and an external anomaly source, which is basically an external data source of natural images, on which basically the two images are blended and an anomalous image is produced.
So once they generate, it generates
So it,
the once you got this simulate anomaly, uh, you also add some Gaussian noise, and then condition on that to generate the recovered image.
I think that should be correct. At the same time, it's passed through the encoder of the VAE to basically produce the latent sample corresponding to the normal image as well as the simulated anomalous image, which would be denoted by C in this case, which would be the latent sample corresponding to this noisy inputs, corresponding to the simulated anomalous sample.
Then what? Then which T should you use? Or you
I
just
think.
yeah, which
Mhm.
T should you use?
I think that's a very good point. In this particular case, I think that as I see in the objective function, the t is basically randomly sampled during the training process. So it's very likely that C noisy is also conditioned basically on that particular time step at which the noise is generated. In this case, I'll also like to say that the process of although it was being conditioned at training time, the exact process of conditioning, the conditioning mechanism was not specified. So it would not be easy for me to say if C noisy corresponding to the same time step or not. So that's one point I think I saw. But at the same time, I think
This
that
is this yeah, this is also in the training, right? That means the training includes not only normal samples but also the interpolated anomaly samples, right?
yes, yes. So that is basically a different aspect for this method, which is that, I mean, a unique aspect, which is that the noisy condition embedding is being passed during the training time. On the other hand, the noisy embeddings are usually passed, or I mean, the conditioned embeddings are usually passed just during the sampling process for diffusion models. So that's one difference I had observed.
Yeah, then my question is how can we use DDPM for anomaly detection?
Yes, yes. So basically, at this point in time, I have talked to you about the training process as well as the generation of the noisy conditioned samples. Um, so in this case, I do have a diagram which talk illustrates this process, and we do see that basically an encoder is used in order to generate the latent vector along with the condition vector. Now,
Mhm.
at the testing time, the condition vector would correspond to the latent vector corresponding to the input image. So that would basically be the case in this case. So, and it's passed through the diffusion process ZTC noisy, and basically the same process is followed in order to produce the intermediate channels. At the same time, I think that we can also, I think I can confirm it from the article itself in this case, but I think that should be, that's, I think my estimation that C was basically just the same as the anomalous sample at sampling time.
But if you use the question is here, like if you use some kind of anomaly images to train a generative model.
Hmm.
Um,
Normal images.
yeah, then for the generation, how do you do that? You just condition on any image uh, on the for the current diffusion model. Then you then you expect that the generated image will have those defects fixed or recover or restored.
Yes, yes. So in this particular case, it is basically conditioning on the noise on the simulated anomaly which is generated from the normal sample at the training time, and that particular condition is being passed in order to predict the noise, and that's how a reconstruction is basically being produced, which corresponds to a normal reconstruction in this case. So that's basically a part of this method, basically, which is to take a normal sample and to produce a normal reconstruction, basically.
Oh, from figure. Okay. So okay. Yeah, that's the case. So if you take a look at this part, uh,
Yes, the ZT basically would be at any time step, so that would be noised, basically.
yeah. So actually they corrupt the latent space.
Yes, yes.
Yeah, they put some denoising unit. Actually, uh, the the image is okay. So you're gonna still reconstruct a noiseless image, but during the diffusion process, you kind of um, add into some anomaly, some embedding from the anomaly images, but you still expect that it could recover the noise. That means like you could recover the original uh, images which do not have any defect.
Yes, I think that's basically the point that is being made, which is that even when basically the network is inputted with a noisy condition vector, which corresponds to a simulated anomaly, which is basically the noisy condition vector here. Even at that particular, even in the presence of such a vector, it's basically able to reconstruct the normal sample. So that's, I think, a point that is being made here.
Okay, so can you go back and I want to look at the formula again.
And at the same time, it's also trying to make sure that it's basically not just a direct copy. So that's another point that's made.
So where does the Z enter um, play in this loss? So I see that in your training process,
Hmm.
C noisy, right? C noisy comes from um, some noisy image over the input sample, right? And
Hmm.
you could also have a Z enter, right? Z enter
Yes.
is like you actually replace the C noisy by Z enter.
The C noisy is basically just a noisy part of the simulated anomalous sample, or basically the condition sample. But in this case, Z inter is different because Z inter is basically an interpolated latent sample corresponding to the reconstructed normally reconstructed latent sample, as well as the anomalous condition embedding. So that's basically the interpolated sample.
Yeah. So basically you change. So basically you actually don't have your Z enter it should be ZR, right? You just crop ZR with some noise and you try to throw them into the um, DDPM network and to reconstruct to recover the noise. But right now
So
you switch from ZR to Z enter, and then you get you get the updated C, then you do the C noisy.
So, in this particular case, as I saw it in the diagram, it says that Z inter is basically being used to feed to the discriminative subnetwork. So, Z inter is basically just an input for the discriminative subnetwork in this case. And the point that was being made was that to guide the discriminative subnetwork, the input to the subnetwork was modified as I think we discussed once, that in DRAME, the discriminative subnetwork had an input image and its reconstruction as the input. But in this particular case, in this particular network, the discriminative subnetwork not only has the input image and its reconstruction, but it also has interpolating channels which correspond to interpolation between the input anomalous image, or it might be an input normal image and the reconstructed normal version of this image. So that's basically guiding the discriminative network according to the authors.
So the Z enter is just used to guide the discriminative network.
Yes, yes, it's
But
basically
for the
used
diffusion
for.
training, you only have this C noisy, right?
Yes, yes, for the it's basically for the diffusion training we had the C noisy embedding.
But the C is the original image, right?
Yes, so in this particular case, during training time, C would be the simulated anomalous latent vector. At testing time, it should be the simulated anomalous image. Yes, I mean it should be the input image.
I mean, in the training time, C is C just the normal images, or could be both normal images and anomaly images.
During the training time, C is basically the simulated anomalous image that is derived from the normal image.
It's a simulated anomaly images.
Yes.
And how do you simulate that?
The simulated anomalous image is basically derived from a particular process which involves blending the normal image and an external data source of natural images. So I have talked about here that during the training process, simulated anomalies were obtained from normal samples and an external anomaly source. An external anomaly source can be an external source of natural images. And those there is a particular formula that most of the authors use in order to blend the normal sample and the external anomaly source in order to generate the simulated anomaly.
Okay,
And
so is the diffusion training only based on simulated anomalies?
yes, yes. So the training at the training time, only the simulated anomalous samples were basically noised and used.
And then
But I think
how does the and is the diffusion model based on the latent representation of those samples, or just the original space?
I'm sorry. It-
I mean, is the
the
diffusion trained on latent space? I mean, after VAE transformation, or they are just trained on the original image data?
Yes, yes. So in this particular case, the diffusion model is trained on the latent samples that are obtained after passing through the encoder of the variational autoencoder. So it is basically trained on the latent vector.
Latent vector. So that means like you're gonna first simulate anomalies, right? And then you throw this image. That makes me confused. Like, do you first do a linear combination of the original images and external anomaly images, then do the VAE to get the latent representation, or you first use VAE to get the latent representations for normal images and for a anomaly image, and then you do a linear combination of them.
I think that's a very good point. In this particular case, the simulated anomalies were basically generated before passing it through the variational autoencoder. So the latent vector corresponding to the simulated anomaly was obtained and the simulated anomaly wasn't generated in the latent vector itself. But
Okay,
that's a very good point. Yeah.
okay. First, do some kind of linear combination, then apply VAE, and
Yes. Yes.
so the goal. Okay, so the diffusion, the goal is try to reconstruct this simulated anomaly, and is the reconstruction is the reconstructed image will for before the sent to the discriminative network.
So I think that's another point, that the diffusion model, the point that the authors want to make is that they want to basically reconstruct the normal sample when basically they are conditioned on a noisy simulated anomaly. So that's another aspect of it. So the training process, we are basically using the normal samples and its reconstruction, and we are conditioning it on the simulated anomaly.
So the discriminant network, I saw that. So the input to this network was modified. Um,
Okay, previous slide. Yes,
yeah. So discriminant produced segmentation maps from the concatenation of the input image is reconstructing the version and
and the
additional
industry.
interpolated channels. Okay. So the idea would be give this give the segmentation map. So the discriminant network will for every pixel it will give a probability, right?
Yes,
And your input will be the input images and the reconstructed version, which comes from the diffusion model, right?
which comes from the reconstruction produced by the diffusion model.
And the additional interpolated channel is are those are like the Z inter, right?
Yes, yes. So those are obtained from the interpolation of the reconstructed normal sample and basically the input sample.
Okay. Um, now how do they train this, right? How do they? Okay, because you're gonna simulate an
Yes.
object, you know where is the map,
Hmm.
where is the segmentation map, what the segmentation map is, so you can just train discriminative network.
Yes,
Uh,
so that's another point, which is that at the training time, it is possible to um, create the mask corresponding to it. So that basically we already have the ground truth mask from the simulation. So from the creation of the simulated anomaly. So that's already provided to us basically.
Okay, this is actually nothing to do with GAN. It's just a discriminate. Well, it's just I would rather say it's a segmentation model.
Yes, yes. So definitely, I think it's a little bit different from the discriminative subnetwork that's used within a generative adversarial approach. So that's
Yeah,
a little bit
it's
different.
confusing. They're we call this one. Okay, and then do they train this uh discriminative subnetwork and the diffusion model altogether?
I think that's a good question. I will try to verify it from fully
Because you can
concretely
also do this
from
step
the.
by step, right? You can first train the diffusion model, and uh, and then from those data used to train diffusion models, you know the diffusion models reconstruction, right? Then you can use that to train a discriminative network. I don't know.
And
Yeah.
I believe that the point that you have made should be correct, which is that diffusion model is trained first, I think.
Okay. Okay. Yeah. Let's continue.
Right. I think that's a little bit of work here. So this is an article on transfusion. This is another very innovative approach on using transparency-based diffusion model for anomaly detection. And the article is a little bit bigger in this particular case because it's a trying to come up with a novel concept as compared to just modeling noise in a diffusion model. The concept introduced by the authors rested on the idea that images can be thought of as a composition of anomalous and normal image components partitioned by the anomaly mask. The
Mhm.
blending factor between the anomalous and the normal image was considered as the transparency of the anomalous component.
Okay.
More, yes, yes.
Mhm.
So, more specifically, the authors took motivation from the transparency factor introduced during the generation of the simulated anomalous images shown below. So, in the previous article, also they used simulated anomalies. In this article, also, they basically took motivation from the process of generating the simulated anomaly, which is with this formula, where m bar basically represent the complement and the transparency of anomalous portions was gradually increased within the framework of diffusion process to reconstruct the normal sample.
So what
So
does M
here,
mean? M is the anomaly mask.
yes, yes, M is the anomaly mask in this case. So that's just the mask, 0 or 1 binary mask. A is the anomaly source, basically anomaly source image that's gathered from an external data set, external natural image source, and N is the normal sample. And m bar should be the complement of it. So in this case, we can see that we are taking the complement of the mask corresponding to the anomaly, the ground truth mask corresponding to the anomaly, and we are doing an element-wise multiplication with the normal sample to get the rest of the normal portion. And then we are doing some type of an interpolation in between the anomaly source and the normal sample with the same ground truth mask, but with different weighting factors. And this is what is termed as the transparency. Here, 1 minus beta is basically the transparency that the authors use.
Okay. Then once you generate such an anomaly, and how so is the diffusion model trained to reconstruct to recover the original image or to reconstruct the anomaly, the simulated anomaly.
In this particular case, the method is a little bit involved because in this case, the diffusion model is structured a little bit differently. Um, but I will basically uh, show the image here, which tries to talk about it. So in this particular case, the diffusion model basically has three different heads, which basically correspond to the mask, the anomalous image, the anomaly source, as well as the this NT is basically the normal source, and these are basically combined in order to produce the actual image, that's XT. So that's basically how it is being done. And as we keep increasing the transparency factor, we try to reconstruct the normal sample in this particular case. Basically, going from the anomalous sample, we keep we increase the transparency, or we increase. Um, I mean, we basically go through a reverse process of diffusion in order to create an actual normal sample. So that's something that's done here. So it's a little bit different in that way.
Let me take a look. Uh,
Hmm.
take the two caption. The training samples are created from normal images X by generating the anomaly mask M anomaly appearance epsilon.
Yes,
So
yes.
here's anomaly appearance epsilon, and imposing the
So,
max according to the transparent schedule beta t.
mhm. and the resulting image xt, which is basically coming from the forward process, that would contain synthetic anomalies. So epsilon is basically the anomaly source image in this case, and xt would basically be the synthetic anomaly that's coming from a forward process.
The transfusion outputs the estimated anomaly mask MT, the anomaly appearance um, epsilon t,
Epsilon t.
normal appearance NT. So it tries to generate all three things together, like the mask, the the anomaly itself, and also the normal image.
Yes, so in this case, it has three prediction heads as opposed to just one prediction head. So in this case, it's generating three samples at the same time, and the loss function is structured, that way basically.
Okay, but the inside the model, the diffusion model itself, it doesn't contain too many components. Just to follow the standard diffusion training process, right?
Um, I think that should be the case. I can show the loss function, which can help in getting the view for it. So that should basically be in the article because the loss function is a little bit involved in this case. So it's a lot of components for every prediction head. So if you would like me to go there.
Oh, okay. So look at here. Similar to how Gaussian noises use the DPMs, the transparency of anomalous images were reduced in a forward process with
So this is the reverse process, yes.
the reverse process.
Mhm.
Um, okay, can you go back? Let me take a look at the formula. So it's the reverse process in the DDPM, right?
Yes, yes.
Then what does beta T mean? Beta T is the transparency.
It is the transparency schedule basically that's specified in this case. So it would
And
basic.
what does epsilon T here mean? Epsilon T is the will epsilon T be changed during the training or not?
So the epsilon t is basically coming from the anomaly source. Initially, the initial specification is that okay, the ground truth, um, normal image, anomaly source, and the mask is used, and then it's basically conducted. I mean, during the training time. At the testing time, I think basically the mask is basically all zeros in that case. So that's a little bit different during the inference time.
Yeah, that's something I feel. Okay, let me take a look. So they schedule beta, right?
Yes.
Is this a beta? Is this beta the same as the one you used to construct a simulated anomaly?
Um, so basically, the beta schedule, from my estimation, I think that's pre-specified. I think
So you have some beta, right? That means like
that should be like the noise schedule in this case. I think, or I remember there's also temperature schedule, usually specified.
yeah. So yeah, this is something confused because when you do the reverse process, right? You're varying t number of steps, right?
Mm-hmm.
And but here, what does it mean by MT?
MT should basically be the mask prediction at the time step t, basically in this case.
And NT, what does NT mean?
And t should basically be the normal prediction at time step t. So that's another that's coming from the diffusion model basically.
Okay, MT is the noisy prediction of the mask.
Yes, yes. So that's the noise. That's the intermediate prediction basically.
Oh, I see. So epsilon T is a noisy version of A.
Yes. So that's basically being recovered in this case. So epsilon t.
Oh, okay.
There was a slight confusion, I remember, during the at the training process. Exactly how they are going in the backward direction. I remember, but I think that was specified by them during the inference time initially.
Okay, can you go to the next slide? We'll take a look at the model architecture again.
Yes. So in this case, I think x, epsilon, and m are, I think, at the initial time frame, they are just the ones that are specified. I mean, the ground truth versions.
And you want to, through a diffusion model, you want to recover MT, epsilon, and NT. Okay.
Yeah. So I think at the end of the process, they should have M as all. I think that should not contain any anomaly. I think
Yeah, the only thing I'm confused, like why do they specify the transparency factor? So the transparent factor is actually um, varying along with time t, right?
the transparency factor is a function of TS. So beta should vary as T varies, and I think that's basically the part of the forward process and reverse process.
So can you go back? Let me take a
Mhm.
look. Then go back.
So this is
Yeah,
just coming.
your anomaly. Okay. So it says the transparency of anomaly portions was gradually increased with the framework of diffusion process to reconstruct normal images. That basically means like in the diffusion process, you're gonna diffuse it to what? To increase the beta, right? Increase the beta means like the normal images are becoming more and more important.
Yes, yes. So beta is, I think, decreased in this case. So that I think the this particular part, the anomalous part, basically goes away. So that was possibly the motivation in this case. Um,
Then in the diffusion process, you also need to add some like noise to mask to A and to N, right?
um, So yes, so I think that's another point, which is that they did not use explicit noise terms in this case, but they basically used prediction heads to predict M and A, basically A being the epsilon in this case. So that was a little bit different because I remember, I think in the normal diffusion process, the noise is predicted. In this case, M is being predicted and A is being predicted. So
So okay, so
so
this model, so this method actually um, also vary the change the diffusion process, right? Like the forward diffusion process is also changed because the standard DDPM you only need to add some like Gaussian noise, right?
yes.
And here they add not only Gaussian noise but also the schedule beta.
Yes, so I mean, it's a little bit, I mean, very different from the diffusion process. I mean, because diffusion process relies on using Gaussian noise. It has a particular structure of going in the forward process and doing a reverse chain, and then trying to predict the reverse chain and coming up with the objective function, which is composed of KL divergences between the reversed forward process and the approximate and its approximate reversion. So that's a I mean, the diffusion process that usually talked about with DDPMs is a little bit different, very different from the one proposed here, because it looks very different. I mean, when I saw the objective functions also.
Okay, so let's see during the training, the synthetic anomalies were created by sampling a random step T using the corresponding transparent factor for this step, the ground truth mask.
The input image and the anomaly source image.
Oh,
And
so they view the beta T as they just view the beta T as noise. I mean, they view the anomaly as noise, right? They don't sample additional Gaussian noise.
yes, I think that's a point being made, that basically beta is being considered as controlling the noise, but I think that it might be similar to something like annealing. Annealing being, where they have a temperature schedule. So I mean, that's how I saw it. So
Using the channel-wise concatenating input, the model was made to predict the mask, the anomaly appearance, and the normal appearance. Okay. Separate the loss functions were designed for each
for
anomaly.
each.
But during the inference, it says like the mask is initially set to all zeros.
The initial mask was basically set to all zeros during inference. Yes.
Okay. So yeah, can we come to the figure again? So every time you just schedule the beta t, right? You have the beta
Yes.
t. You don't add any noise to any of them. You just
There's a transparency schedule which is beta t, so
yeah,
that's
yeah.
different.
That's a transparency schedule. Beta t,
Mhm.
you got your uh, but you still have your mask, right? Your mask doesn't change. It,
Yes, I mean, the mask is being predicted here also.
also, it's just to predict the mask.
Yes, so the mask is concatenated, and then using the diffusion model, the prediction is made. So the input is also different in this case. It's not just xt, but it's mt plus 1 and xt.
So then
And
when you do the inference, how do you do that? Your mask is zero.
uh, I think that's a good point. So the mask initially was basically set to zero. So that definitely means that the initial mask, that is all zeros, were concatenated with the initial input, basically, which would be an anomalous image or a normal image, a test sample.
But then every time you generate xt minus one and mt, and then you throw them into the model and do this again, right?
Hmm. And from here, basically, xt minus 1 would be derived using the formula that's present in the previous slide. So,
Yeah, the question is during the training you don't change m. No, actually you change, right? If you I
yes.
mean during the training procedure, if your mask, if your conditioned mask is not changed, you won't be able to um you cover the mask, right?
Yes, yes. So I think
How do
the
they change the
thing,
mask?
yes, I think that in this case, that's where a confusion arose, which is that they said that initially the mask is the ground truth mask. So if it's already the ground truth mask, then how is it different at further time step? Because it might just be an I mean, so that's where.
Yeah, maybe I can understand that. Okay, you use every time you use anomaly creation through beta team. That's a schedule,
Hmm.
and you
Yes.
want your noisy, your new anomaly, which is XT, and how do you get MA? It's called pre-mask simulation. So that means like you have some kind of like simulation to corrupt M, right? What's the
Yes.
Yeah, what does it mean for pre-mask previous mask simulation?
Yes, so that's I think something I think possibly they're talking here, which is that transfusion is guided by an augmented mask MA. So
Okay.
that's a little bit different, I think. That possibly can be verified by me, but I think that that's where a little bit less description was present. So I mean, re-verify if that's
Okay.
something what
Yeah,
they are
but the
talking about.
framework is clear. The framework is clear. Oh, yeah, that's interesting. So basically, you want to use diffusion model to predict not only original images but also anomaly part and also the mask.
Basically three different predictions being made in this case and the normal component.
Yeah, and then through this combination, you can create um, another anomaly image.
Yes, yes.
Yeah,
So that would basically be the xt minus 1.
yeah. Okay, interesting. Let me,
um,
which place is this paper published?
that I'll definitely add as a subtitle here. So I think those ones I'm still in the process of adding because I was refining the slides also, the later slides that I was adding. So
Yeah,
that I'll definitely make sure to add in this case. um,
yeah, let's move on. Yeah.
Yes, so I think this is another article which basically uses conditioning, which is a different type of conditioning in this case, and it's diffusion AD, which is norm-guided one-step denoising diffusion for anomaly detection. In this case, the authors introduced a two-stage anomaly detection pipeline consisting of a reconstruction subnetwork and a segmentation subnetwork. So it is similar to DRAME in that aspect. The reconstruction subnetwork consisted of a denoising diffusion model. A norm-guided one-step denoising paradigm was introduced to alleviate the computational cost of performing a full inference with the diffusion model. So instead of coming up with a full iteration of the reverse process, in this particular case, they are basically only doing a two-step denoising. So there's just two steps that they're using. Um, the standard procedure was followed to train the diffusion model on the distribution of the normal samples. In this case, basically, the noise prediction was basically being used as an objective function to train the diffusion model. The diffusion model and the segmentation subnetwork were jointly trained. During inference, at any point in time, the reconstructions could always be obtained due to the nature of the parameterization of the reverse process in DDPM. So this is a particular advantage of the DDPM model that that the authors are taking in this case, which is to say that more specifically, the following expression gives an approximate reconstruction given a noise prediction and the noise sampled at the current time step. So this is just basically an advantage of the reverse process that they are taking and the way the reverse
Okay.
process is
So
structured to give a prediction.
is this model like using anomalies for training, or is it just to use the normal samples for training?
At the training time, I think the process was basically to use the normal samples and to predict the noise using the normal samples, basically.
And then the segmentation subnetwork is just the places where you have. Then the problem is like if you use Gaussian noise, right? The noise is everywhere, right? How do you train a segmentation network?
How so? Let's take a look at the in this case. Yes, yes, I think that's a good point, which is that how is the segmentation subnetwork being jointly trained? So I do remember that as far as the diffusion model is concerned, that was having an objective which was a simple noise objective. But there was a particular process through which they were doing norm guided one step denoising. So that was basically something that was a little bit unique as far as uh, this model is concerned. So
For norm guided one step noising.
yes, yes. So I do understand I do understand as far as the norm guided one step denoising part that was being used here. So
But where's the segmentation network? And why is there a mask?
um yes, so I think that's a good point. In this particular case, I think they might be using a simulated sample if basically they are having a particular mask with an output. So that might be the case here as
Oh,
well.
the mask. Okay, the mask is not okay. Then that means like your image for the diffusion model also contains some kind of anomalies, right?
That should be the case. In this particular case, they were using a two-step process in order to predict the image, basically. So let me see. I should have a description here.
Yeah, you can go to the next one.
Yeah. Yes, yes. So this was basically a part of the inference process where during inference, the random range of times between 0, comma t were divided into two parts, S and B. Following procedure was then followed. An input image was perturbed using two randomly sampled time steps, TS and TB, from two partitions respectively. So the authors basically make a point over here that we can perturb the input image using small noise, or we could perturb it using larger noise. In the case when basically the anomalies occupy a very small area in the image or are not very pronounced, there can be a reconstruction that can be performed from us by adding small noise, and that might just give us a normal sample, which is also not having any distortions in the normal areas. At the same time, there are also cases where the anomalies occupy a very large area, I mean, a relatively large area in the image. In that case, we need to basically perturb it with a larger amount of noise and then produce the reconstruction, so that basically we have a normal sample. We have normality restored image in this case, or a normal appearance that occurs in the image, but that might have certain distortions in the already occurring normal areas. So that's where basically they had a two-step guided process that they used, where they first perturb it using two randomly sample time steps, one being a smaller time step and the other being a larger time steps from these two partitions. And then the noise corresponding to the time steps was then predicted. That is, both for these two time steps, the noise was predicted using the diffusion model that was trained on the normal samples. Anomaly free prediction was made for the later time step XTB. So first, basically, we have a larger noise time step where we had did a larger amount of noise, and we made an anomaly free prediction for this particular later time step. The anomaly-free prediction of the earlier time step (xts) was conditioned on this later time step (xtb) to obtain the norm-guided anomaly-free reconstruction. So in this case, the noise prediction was basically being conditioned on the later prediction in order to come up with a norm-guided anomaly-free
What does it
reconstruction
mean for
corresponding.
guided anomaly free reconstruction? So you have
I'm
a, yeah, you got noise, you got two time step, right?
hmm.
And this is inference, right? So you can
Yes.
we can think about that. We kind of like infer what will the image be at the first time step and second time step. But why it says like anomaly free prediction was made for the later time step as TB? The later time step should be corresponding to the more noisy one, right?
The later time step should correspond to the more noisy one, and in this case, it might have distortions. So that's where we are using the XTS time step here. Yes, so that's a good point. But at the same time, the point that was being made by the authors was that the later time step, because a lot of noise was added to the image, the reconstruction will basically show a consistently anomaly-free prediction, or or a consistent normal appearance, which may not correspond to the input normal appearance, but still it will be normal appearance that will be reconstructed. So that's the point that was made by the authors in this case.
I'm still not following you. So what does it mean by anomaly free prediction was made for the later time step? Is it like starting from noise, from pure Gaussian noise, and then you go through, you do the inference, right? That means you sample at step by step until you reach TS and TB.
Hmm.
So then that means like of course the image at TB should be closer than the image at TS, right?
Yes, so the TB image will have more noise as compared to the TS image as we are going in the forward process.
Mhm. And
And
then
so
it
it
said
should
the
be
anomaly
coarser.
free prediction of the earlier time step XT and TS was conditioned on this later.
So the conditioning process was being made to ensure that the TS image doesn't, the reconstruction of the TS image doesn't contain anomalies, but I mean, it's being conditioned on a normal, I mean, on a normal appearance in this case. But at the same time, we also have a prediction that's being made for this time step TS, which will be a little bit more fine grained prediction corresponding to the normal areas in the image. So that's the point being made.
So basically you are conditional XTB and then you run the inference until you arrive at XTS.
So in this case, they are not basically running an iterative process in order to come up with the prediction. They are just having two time steps at which they are making the prediction. So in the previous slide here, they are basically using this formula in order to make the prediction. Here xt can be replaced by xtb, and epsilon theta xtb, this will be a tb and tb. Um, at the ts time step, the noise prediction would also be conditioned on the prediction that we have basically made for the coarser image. So that would also include XTB along with XTS in this case. So that's where that's the point that's being made. So it's being
How
conditioned
do
on the
yeah,
later time step.
if you concatenate like this, how do you get to the mask?
Yes, yes. So that's another point, which is that in this case, the conditioning wasn't done by concatenation, but it was basically being done by taking motivation from the equivalence between DDPM and the score-based model, which basically uses the gradient. And from that, basically, a formula is derived in order to make the noise prediction epsilon theta of XTS. So the detailed formula, let me see if I did add it here.
That's yeah, I'm confused because look like you have the mask beforehand, right?
Hmm. The mask, which one here?
Yeah, you looks like you have the mask, right? You have the mask,
Um,
and
that's a good point. Yes.
you just leverage the diffusions. You got two predictions from diffusion, right? And
Yes.
you concatenate them together to predict the mask. That's it.
So in this case, the input was basically the input image, which was the input anomalous sample, and the anomaly free restoration at the finer level, basically, that was obtained after we had made the reconstruction prediction for xt. I think for this is the xts prediction. So I mean the initial prediction coming from the finer image, so finer noise. So those were concatenated, and then this was passed through the segmentation subnetwork. So this would be a normality restored image in the author's opinion, but this would basically come after the conditioning process. So
So my understanding is that from this figure, your training of diffusion has already included the noisy images. I mean the anomaly images. So if you take a look at the top left, it actually contains the image. And also you have the ground truth mask.
on the top left, yes, yes, I
Top left.
think that's yeah.
Yeah, and you just train a diffusion model, and the diffusion model is it has like some normal guided one step denoise whatever. But you train some diffusion model, right? You train a diffusion model, and then once it's down, like you train the segmentation subnetwork, right? The segmentation subnetwork, the input to this UNet contains like original input and the prediction made by the diffusion model,
Yes.
and then you predict mask. That's it.
And then we predict the mask. Yes. So I mean the prediction made by the diffusion model would also be the image that we got. So and that's basically we are predicting the mask here and doing the loss function. But in this case, basically there would be a two-step. That's where this NOD is coming here. So also the conditioning process is not done at training time as we had observed in the one of the previous articles, but the conditioning process is done during the one-step denoising time. So that's another part. I mean during the sampling time of the two-step process.
Why it is called norm guided one step noise?
I
What does
think
norm guided?
yes. I think the term norm guided they take in order to basically talk about the different levels of noise or the different norm of noise that they are using in this two-step process. One being a larger norm noise and the other being a lesser finer noise. So noise at a lesser scale or with a lesser norm.
But during the training, it still uses the it still uses like the original training, right? You just like given the current noisy state and time t, step t, you just predict, just try to recover the original image, right?
Yes, yes. I think that's basically a part of this method, which is that basically initially we make this unconditional prediction, which is coming from the diffusion model directly, which is just on the basis of the trained diffusion model. But the XTS prediction is basically being made with a certain guidance or with basically a conditioning mechanism in this case, which is coming from the previous image, XTB. I mean, X not B, this one.
So what does it mean for NT? If you look at their norm guided one step noisy, you got epsilon theta XTS, which I can understand, right?
Mm-hmm.
Trying to predict the noise at step T, TX,
Yes.
and you got epsilon theta XTB is a step, is a noise at step TB, right? And then what does it mean for epsilon theta XT S and NT? What does NTS mean?
Yes, so I think that's another point which they made that once they basically had a normal reconstruction that they had obtained from the time step TB, that is XTB, the noised image, then we basically have a normal appearance or a normality restored image at this time step, which is X naught hat B or N. But then the authors say that they want to basically further noise it basically before being putting it as a condition into the noise prediction process so that the two images basically have similar contents of noise and I mean the only the relative contents are being compared in this case. So that's the point that was being made by the authors, which is that okay, once I have a normal appearance, I will again noise it with a certain level of noise or with a noise prediction which come I mean with a noise prediction that comes from here epsilon theta xts, and then use it as a conditioning input.
So that one is what does this last symbol mean? Is NTS or NT? NTS, right?
Yes, so that would be nts, that would basically be the noised version of x noised version of n at time step ts.
But
And
then you have
yes.
one additional input to epsilon theta, right? Epsilon theta is network. How do you? So basically, epsilon theta, they normally they receive t, right? They receive time step. They receive
Mhm.
the noisy state, right? So now you have one
Yes.
additional input. How do you put them into the network, right?
Yes, so that would basically be modified. We have epsilon theta xts comma nts that would basically be modified based on the gradient step that's usually taken and the equivalence. There's a particular term for it, which is um, there's a particular term that they used for this particular conditioning mechanism. Um, I think there's some sim similarity function basically that they use. So
So basically, they
uh,
combine NTS and XTS together and to form one to make sure that they fit the network epsilon theta properly.
in this particular case, they would basically condition it on NTS to ensure that I mean, it's basically, I mean, there is not that much difference between the two images, so that's motivation in this case. Um, but at the same time, XTS also has to not have the anomalous areas in it. I mean, also needs to have the areas which are normal being predicted well. Um, so
Yeah,
that's
my point is like this. So how can I make the comments? Um, this one. Why I can't make any comment?
yes, yes. I think I can just take the screen and see if
It's weird. I mean, I want to draw something on the.
yes, yes. I mean, I can. I will see. If, I think I remember you were using the G board last time.
So just some like pen in our screen so I can draw something. That's where it disappears.
Okay, let me see. I remember you had the whiteboard last time, so maybe we could use that.
Okay. So I'm gonna use the whiteboard.
Yes,
A
yes.
question is that your epsilon theta is a network, right?
Mm-hmm.
Standard diffusion, you're gonna receive three input T and XT, or two input T and X. You can
Right.
you try to recover the noise at T step, and then you combine XT and epsilon T, you can get the estimation of X0, right? That's a diffusion.
Yes, so that should be basically we are getting the estimate of x0 here. That's coming from
Then in that paper, the figure shows that okay, you have epsilon theta, right? So they
right.
kind of omit this T, right? So basically they said, okay, now my network can receive not only XT, but also they call it XTS, but also called NTS, right? So that means you increase the number of inputs to the neural network. How would that be possible, right?
Yes, so in this case, the number of inputs that's not how they are basically coming up with it in this particular case, which is basically by modifying the formula of epsilon theta xts, which is saying that epsilon theta xts minus some gradient term basically that's coming, which in this case is just xts minus nts after we basically take the gradient with respect to.
Oh, I see. Okay.
Um,
Basically, they first combine them together through some, see, just subtraction.
Yes, yes. But I think your point is very valid that it could just be an input to an, I mean, if we have to learn from the relative difference of these two. So,
Now, how do they get the NTS? The NTS comes from the difference between the noise at the TB and TS, whatever.
NTS basically comes from the, basically first we predict N, which is XTB, X naught hat B. I'm sorry for the drawing. Uh, B, and then we basically use the epsilon theta of xts that has been predicted in order to add noise to this end, and we use and then we get the nts basically. So n would just be the reconstructed image at time step tb using time step tb.
Is just a reconstruct image using time step TB.
Yes, yes, using the noised image at time step tb, so that's how. we are basically coming up with an x naught hat b that I had in the slides.
If
Uh,
n,
mm.
then what does it mean for NTS? NTS should be the noisy image at TS, which is XTS, right?
Yes, yes. So NTS should basically NTS would come from first we are basically making a prediction of a normal image. Basically prediction of a normal appearance using the time step TB, which is basically X naught hat B, that is the reconstructed image that is coming from time TB. Then we basically, since we also have a noise prediction at time step TS, which is epsilon theta of XTS, uh, um, which is standalone using the diffusion model. Uh, it's like my drawing is a little bit weird. So then we basically use it to noise n also. So then we get NTS basically.
Use what?
Use the noise prediction in order to add noise to n, which is the prediction at time step TB using time step TB.
So I mean, I use time step TB. The
Mhm.
reconstruct the image at time step TB,
Mhm.
the ground truth, and then corrupted by my predicted noise at TS to get NTS.
Yes, yes. So it's basically the predicted noise at TS, which is epsilon theta of XTS.
Mhm.
And N is not the actual image, but it is basically the normal appearance that's predicted from time step TB, or I mean the
And then
reconstructed image.
you use time step TS to corrupt that.
Yes, yes. So then we use the time step TS basically to add noise to it so that the authors say that that's another point as to why that's necessary, but it's just that they want to make sure that both the images have same level of noise, so that's um,
Will that help remove the anomalies in the reconstruction?
I think when I'm basically taking the difference of XTS and NTS, and if I have added epsilon theta of XTS to it, then I am basically um, removing, um, removing the anomalous areas somehow. So, um, the anomalous areas that are being, um, hidden. So I will need to think a little bit more about it. So XTS minus
But this
epsilon.
motivation should be like trying to at least reduce the anomaly part in the reconstruction, right?
Yes, yes. So it's basically trying to reduce. Trying to noise the anomaly part. I think um, basically using the noise prediction that's being made. So that's another point, basically,
Okay.
which
Otherwise,
is
I cannot figure out why do they propose such a heuristics, right?
yes, yes, yes.
And
Which
then
is that
if you can exactly reconstruct the the anomaly image, then it will be the same as the input image to for the segmentation network, right? That what's the
mhm,
point for the for that, right?
right. So you're saying if basically you just put the n into this here.
Yeah, I mean, if let's go back to the slides, right?
Okay.
Yeah, if you take a look at that, if you take a look at their segmentation network design,
Mhm.
I can share the slides.
Yes, yes. I think that I had moved the screen. So let's see. Yes. Can you see the slides?
Yeah, yeah. If you take a look at that, right, your input contains two images. One is the original anomaly images. One is from the reconstructed images, right? If they are
Hmm.
exactly the same, then how is possible that the segmentation network can find the mask? Right? You get my point?
So one is which the first one is the reconstructed image that I have here. X naught hat G, and the second one.
Yeah, the first one, if you look at the segmentation subnetwork, the input has two images. One image is
Yes.
the image, right? It contains some anomalies. The other image
Yes.
is a reconstructed image, right? If this
Yes.
reconstructed image is exactly the same as the original anomaly image, then there's no difference between the two inputs, right? The UNet is
Yes.
able to discover the mask.
Yes. In that case, the mass should be zero, basically.
Yeah. So that's why I kind of like I think there are norm guided one-step noises just try to at least reduce the effect of anomaly part.
Yes, yes. So, I mean, in this case, the point is basically to make sure that if there is a lot of difference between the normal reconstruction and the anomalous image, then that's basically, a reason for it to be an anomalous image, or a reason for the pixel to be anomalous in this case. So,
Yeah, yeah, yeah. That means like you must make sure you must encourage your diffusion model to reconstruct the image, which is a little bit different from the original image, right? And those differences should indicate the anomaly part.
yes, yes, that's encouraged by the diffusion model, or I mean, in this case, the norm guided one step denoising process, basically, which is
Yeah.
coming from the trained diffusion model.
Okay. What else about this paper?
Let me see. I think that's a good discussion so far. Um, and okay, to make the mask prediction and the following expression.
Yeah, I think this paper is done, right? So what's the next?
Yes, anomaly detection with condition denoising diffusion models. So
Okay.
I'll
Yeah. Grab, I don't think I have time to continue the discussion, but there are only how many slides are left?
I think it's 10 slides, I think
Yeah,
around
let's
20.
discuss about them next week.
Yes,
But
yes.
now, yeah, but right now we should think about some kind of idea because those diffusion models we have seen a few, right? We can think about how to leverage how to propose our own method to for anomaly detection. One is that we can consider flow matching, right? Not the not just the DDPM.
Yes. So I'll just stop sharing and I'll write it down actually, your suggestions, so that.
Yeah, yeah, yeah. And second thing that we probably want to yeah we want to develop a new approach, right? But this those methods just trying to um like when you using diffusion or generative model to
Mm-hmm.
reconstruct an image, and there should be some like difference, uh, which are indicative for the defects or anomaly part.
I think that's basically the primary motivation.
Yeah, 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 yeah. We can think about how can we adjust this kind of idea in the flow matching model, but or some kind of new method based on flow matching because flow matching is way faster than this than DDPM.
Score matching.
No flow matching, not score matching. Score
Okay.
matching is no difference from DDPM.
Okay.
Yeah.
I think that should be a good point, and I'll basically try to dig into it also along with your other conceptions that you had of the methods from the discussion. So
Okay. Yeah. Yeah. Let's continue discussion next week. But right now, I think we should start thinking about our own method.
yes, yes, I think I could just also try out a GitHub repository in any case and see.
Yeah.
That's something I was planning to. So I'll take a look at that. So
Okay. Yeah. Thanks.
sure. Thanks.